Hi everyone, thank you for coming. So I'm gonna talk, well, the talk that I'm gonna do now basically is trying to answer this question: can flies help us understand sleep? But first I'm gonna talk a bit about me. This is not working. Yeah. So who am I? So my name is Laura, and for my undergrad I did an MSci in neuroscience in UCL. And last year I came to Oxford and I started my PhD in neuroscience. So now I'm just starting my second year. My pronouns are she, her, and I am the L in the LGBTQ+. And why am I doing this? When I started to do internships and going to work in labs during my undergrad, one of my biggest fears was being gay in science, because somehow it seemed like there were no gay people in science. So I thought, oh, maybe just scientists can't be gay, so maybe I should just not do this. And actually that's far from the truth. It's completely not true at all. There's many people here, many of us are scientists, I think. So the problem, as you were saying, is just that there are no role models. So by doing this, I'm hoping to just show that, yeah, there are gay people in science and there are women in science, and you can be a scientist and LGBT. But now the important part, the science. So, as I said, I'm going to talk about how we can use flies to study sleep. But maybe you're thinking, why would we bother about studying sleep at all, right? So, as you can see here, sleep is conserved across across the animal kingdom. Pretty much all the species show sleep. We sleep, but also our pets sleep, and these cute dogs sleep, but also like things like flies and worms sleep. And probably you've experienced that if you don't sleep for a few nights, you feel really, really bad, and maybe you even are more prone to getting ill. And actually, there's some experiments in flies and rats that if you completely sleep deprive the animals, they actually die, as bad as it is. So sleep is very important, we all know that. And probably many of you know that sleep is associated with many disorders, including mood disorders like depression and diseases like Alzheimer's and many things. So basically, sleep problems can cost the economy millions. So it's very important that we understand how it works. So what are the processes that regulate sleep? This is the next question. So sleep is under two processes mostly. So one of these processes, how is it?
Is the bottom one. Yeah.
So one of these processes is the sleep process, which is the circadian regulation of the sleep. This refers to the time when sleep happens. So humans, we are diurnal, so we are awake during the day and then we sleep at night. And you've probably experienced jet lag if you fly to America and then you come back. And it takes a while to adjust to the new timing of the new place where you go. So this is the circadian regulation of the sleep. And we know a lot about this at the molecular and cellular level, but we know very little about this other process, the S process of homeostatic regulation of the sleep. And what is this? So probably you have experience if you decide not to sleep for one night, maybe you have an assignment to finish, or you just go partying or something. The following day, you need to sleep a lot to compensate, and if not, you probably feel really bad. So this is a homeostatic process. So the more time we spend awake, the more our need to sleep increases. And we know very, very little about this, and this is what my work is about. And how can we use flies to understand how sleep homeostasis works? Well, first, you're probably thinking now, but do flies sleep? They can't sleep? Well, they do. And how do we know this? Well, flies have periods of inactivity that are rapidly reversible. So this means that it's not like they're in a coma and they don't wake up. They have a specific posture during this time, and they have an increased arousal threshold. This means that as you need a really loud alarm in the morning to get up, they also need a very high stimuli to be responsive. And very important, these periods of inactivity are under circadian regulation. So just like humans, flies are diurnal, so they sleep during the night. And actually, they even have a siesta in the middle of the day. Yeah, I know, it's funny. They might be coming from Spain like me. And then, very importantly, they also show homeostatic regulation of the sleep. What this means is that if we sleep deprived flies for one night, the following day they're going to sleep a lot more to compensate for this. And this is what I studied. In addition to this, okay, they sleep, but why are they such a good model to understand the circuits and the molecular and cellular mechanisms that regulate this? So here you can see a human brain, and here you can see a fly brain, and the fly brain is several orders of magnitude smaller than the human brain. The human brain, you can see here, it has billions of neurons, and the fly brain only has around 1,100 neurons. It sounds like a lot, but in comparison is nothing. The human brain is, and even the mammalian brain, such as rodent brain, is very complex. There's a lot of connections, so it's very hard to understand things at this level. While the fly brain is much easier to understand what's going on at the level of one neuron. And in addition to this, why the fly is great as a model is because we have tools that allow us to target very specific neuronal populations. These tools cover pretty much the entirety of the neurons in the brain. So here you can just see some examples of labeled neuronal populations. What this means is that if I'm interested in a specific populations of neurons, I can use these tools to gain access to them. While in other models, while there are similar tools, it can be so specific and it doesn't cover basically the entire brain as we do with the fly. And once we have access to these neuronal populations very specifically, we have great tools that allow us to manipulate the activity of neurons or do other things and figure out what they're used, what they're for, what is their role. So if there is a neuron that I think might be involved in regulating sleep, I can use these tools to target them and to have access to these neurons, and then I can use techniques like optogenetics, for example, to activate them and see what happens in the animal. I don't know if you've heard about optogenetics before. So, well, if there was any neuroscientists here, they would know. It was called the breakthrough technique of the decade. Is what my lab is famous for. And basically this technique, what we can do with this is that by shining light into the animal or the animal brain, we can activate, in combination with some genetic engineering, we can actually activate the very specific neurons that we're interested in, and we can see the behavioral effect that this has on the animal. So can you put the video on? So you see now when the light is on, the fly completely freezes, and then when the light is off, this just stops. And it's not because of the light, because we have controls that is the same thing. The light is going on, they have the same, everything that is happening is the same. The only difference is something that is expressed in their brains that allow this light to activate these neurons. So basically what we're doing here, this is not my work, but it's just from a colleague of mine. So this is probably activating some circuits that are important for movement or something like that, and we literally can freeze the fly. So it's a bit like crazy, yeah. But yeah, it sounds a bit crazy, but don't think of it as what a crazy scientist wants to do to control all of your brains here. It's more to figure out what neurons do and how we can use this to understand what is going inside them in relation to behavior. And now back to the And this is just another video that you see a fly. This is a kind of experiment that we do in the lab. It has a cranial window, and then we can shine light on the fly. And the fly is walking on this sphere. And by measuring the movement of the sphere, we can figure out whether it's asleep or awake and how much it is sleeping. And we can see the effect of activating specific neurons, and then we can also record from neurons and figure out the molecular mechanisms that are regulating these processes and how this correlates to behavior. And doing this kind of work, my lab has found some neurons in the fly brain, like this pretty, in my opinion, pretty neuron that you can find here, that basically it works as they call it as the output arm of Drosophila sleep homeostat. What we mean by this is that these neurons, if we activate them, they induce sleep. And these neurons measure sleep need. So as the day progresses, or as the fly is more tired, these neurons become more excitable. They are silent just when the flies wake up and when they are very active, and then as the day goes and they're more tired, their activity increases until a point is reached that basically the fly will go to sleep, and then the process goes again, this cycle. And you're thinking, okay, this all sounds great, but does this matter at all for humans? Like, we don't really care about flies, right? So, well, in humans, there's actually a population of neurons in the hypothalamus, in the ventrolateral preoptic area of the brain, that it seems pretty much in function homologous to this population of neurons in the flies. And of course, the fly brain and the human brain are very different, but as it has happened with the circadian regulation of sleep, that I've told you that we know already a lot. The Nobel Prize was awarded to this field last year, and most of the work was done in flies, and then it was shown that it's pretty much the same in other models, in mammals, etc. So basically what I'm trying to say is that the molecular and cellular mechanisms of how things work are often conserved. So it is very likely that by understanding how these neurons work, we can understand better in the future how perhaps these neurons in mammals and humans work. Just thank you everyone for listening and for coming, and if you have any questions, feel free to ask.